Ladies and gentlemen, today's class recording has started. So, yesterday, we introduced the concept of work. And in order for there to be work done in a system, there's two things that have to happen. One, there has to be a force applied to that system. And two, there has to be some motion that's involved with it. And that leads us to our definition of work, or calculating work as the product of force and distance. But then we discussed that more important than what work is what work does. And work results in a change in the energy of a system. So when we have work done in a system, it results in a change in its energy. Kinetic energy, yes, but that can also be potential energy as well, because we said potential energy can turn into kinetic, etc., etc., etc. So today, what I want to start with is looking at a couple of examples how these two definitions of work apply to some physical systems, how we can use both of them depending on the situation, and so we'll start from there. All right, so the sheet I gave you today starts off with just some identification questions, and the question is always the same: is it work? So, adjust this a little bit. There we go. All right, so we have five pictures here. Situation number one: is it work when a pitcher throws a baseball? Yes, right? If we look at both definitions, one, does the pitcher apply a force to the baseball? Yes. Does it move because of the force? Yes, so that fits that definition. Second, does the energy of the baseball change because of what the pitcher is doing to it? Yeah, I mean, right, it starts with zero kinetic energy, and then after he throws it, it has more than zero kinetic energy, so there's definitely a change there. All right, so is it work when a pitcher throws a baseball? Yes, it is. Exclamation point. Make sure you include the exclamation point, so because that's important. All right. Next, we have two different pictures of somebody catching the baseball. All right. The details are not as clear on your sheet as they are up on here, so let's talk about the two situations. First, is it work when somebody catches a baseball? Yes. More specifically, what kind of work would it be? Negative work, because we're decreasing the energy of that baseball, right? It's moving before we catch it, but it's not moving after we catch it, okay? So in both of these situations, the answer is yes, because the energy is decreasing, right? A decrease in kinetic energy, and that's negative work. But the reason why there's two pictures here is to illustrate some of those things that contribute to work. So we said that work is done if there are two requirements in order for work to be done: force applied and distance the object moves. Okay? So in the first picture, the one on the left, I don't know if you can tell from your copy or not, but the little whoosh lines are illustrating that when that ball was caught, the person catching it sort of took their hands and moved backwards while we were catching the ball. Kind of like when you're catching the water balloon at the family reunion water balloon toss, right? You know, you take that, you take the long cradle, right? Okay. In this picture on the right, the person just holds their hand out like this. The ball strikes it. Okay. What? Yeah, you can kind of see, I don't know if you can see from the picture up there, or I don't think you're there. Notice that the hand is very red in the picture on the right. Okay? Yes, Sean? Under most circumstances, I agree with you. It's just not, like my mom's family, I'm half Italian, and so like it's not just the family reunion, it's like, it's literally like a production. Yeah, like I don't. Yeah, well, imagine that happening, but I'm 41 years old, so it's like my mom's cousins are like, I remember when you were. I'm like, great. Now I have two kids, so so yeah, it doesn't get, so just so you know, it doesn't get any better. So I really hope my mom doesn't watch this recording. Hear me saying all these things, but so. Which was like my brother and my sister who both live like in different states, and they're like, oh, I can't come, sorry, but anyway. So in both situations, well, let's talk about the one on the right and why it's horrible to catch the ball just by holding your hand like this, right? Because it hurts, right? In order for work to be done, right, two things have to happen, force and distance. In both cases, we are decreasing the kinetic energy of that ball from whatever velocity it was going when it was thrown to 0. So work is being done. But we can do it in two ways. Here, the person catching the ball starts catching it here, and then the whole way back, they're bringing it to a stop. We are increasing the distance over which that ball is being brought to rest. We are increasing the distance over which the energy is changing. If we have a greater distance, how much force are we going to need to use? More or less? All right. In this case here, the change in kinetic energy is going to be the same in both pictures. So we have two options. In this picture, the distance is increased. But if the distance is increased, that requires less force. Why? Because we have a longer distance over which we're trying to accomplish something. In the picture on the right, though, right, the only distance is how far your hand compresses when the ball hits it, right? So in this case here, the distance that the ball is being brought to rest is very short. If distance is small, how much force are we going to need? Well, hope you can see the pattern from blue to green, right? With big distance, we needed less force. With small distance, we're going to need how much force? I know, it's Wednesday. I know, it's only Wednesday. So, if we have a smaller distance, we have an increased force that is required, right? What kind of relationship are we talking about here? One's going up, one's going down, right? Inverse relationship, right? That's only true because in both situations where we would be doing the same amount of work, right? So that's when the inverse relationship is going to show up, okay? Good there. Okay with that? All right. No, let's not even go there. So I won't even take you down that road. So. I was going to say, like, if you were catching, regardless of how you caught it, if you were catching a softball, which is bigger, how much work are you doing there? More work or less work? If you're catching something that's bigger. More work, right? Because a bigger object has greater kinetic energy, right? So we still have to bring it to rest. So something bigger would require more work. And that would require more force and possibly more distance, depending on how we're doing it. Okay? All right, next picture. Guy pulling big slab of marble. We talked about this yesterday. Is work being done in that situation? As long as we assume that what is not happening. If it doesn't move, then there's no work, right? So in this case here, assuming that there is no motion, which is what I'm trying to get to you there, right? No work is being done there. Okay? The next picture can be a little tricky if we don't put a condition on it, right? So, I have this cube of aluminum, right? I'm holding it in my hand like this as I move it around the room. Am I doing work on it? No, right? So, two things we can think about it, okay? One, my hand is pushing on the block of aluminum which way? Upward. Which way is the block of aluminum moving? Well, now it's not moving at all, right? But if we're like I'm carrying around this way, right? So as the arrows are indicating in the picture, what's the angle between the direction of movement and the force that's being applied? 90 degrees. And if we go back to our formula from yesterday, right, cosine of 90 is 0, right? my hand is not changing the energy of this block. But it is changing sometimes, right? Especially if I go like this and stop it, right? So is my hand doing work? No. Is friction doing work? Yes, right? There has to be work if it goes from not moving to moving, all right? But they're trying to get you in this picture here that the force of my hand pushing upward on this block is not doing any work because it's not acting in the direction of movement, all right? So in this case here, this would be no as well. All right, good there? All right, so let's take a look at this next conceptual example that involves an accelerating car. So it says, and this is the kind of question that shows up like on multiple choice sections of standardized tests all the time. No numbers, just relationships, right? So let's keep in mind what we're looking at there, right? It says, to accelerate a certain car from rest to the speed of v requires work w. Is the work required to accelerate the car from v to 2v equal to w, 2w, 3w, or 4w? All right? So, in order to attack this problem, I want us to look at three separate things. All right? We need to analyze the velocity of this car, we need to analyze the kinetic energy of this car, and we need to analyze the work that is done. Okay? Good there? Right. So, what does it tell us about the velocity of the car at the beginning? Alright, what's the initial velocity of the car? 0. Right? And then it says that it accelerates from 0 to a speed of v. And then a little bit later on, it accelerates from v to 2v. Okay? Good so far? Alright. Next, let's look at kinetic energy. Okay? First, if there's no velocity, what's kinetic energy have to be? 0. Right? So there's going to be no kinetic energy at the beginning. Right? Now, we don't have the mass of this car, all right? So we can't actually calculate its kinetic energy, but does it have kinetic energy in the middle picture? It's moving now, right? So let's just call that KE. We don't know exactly how much KE it is, but we know that it has kinetic energy, all right? But now we can make an assumption about the kinetic energy at the next section, or the last picture. How much kinetic energy will it have at the next picture? It is 4 times, because what are we doing to velocity in that kinetic energy formula? Right? Quadratic relationship. So here, we're not going to have twice as much kinetic energy. We're going to have 4 times as much kinetic energy. Okay? Good so far? All right. Now, work is going to be a little different. Can we have work, a work value in each of the 3 columns like we have for velocity and kinetic energy? What does work do? We go back to our definition of yesterday. What does work do? When there's work being done on an object, what happens? True. Its energy changes, right? There has to be force and it has to move, but because of those 2 things, its energy changes. So if we're looking at the change in something, can we look at that at one specific spot? If we're looking at change, we need to know 2 spots, right? Because we need to know how much it started with and how much it ended with. Does that make sense? All right? So, from here to here, it tells us that there was, to go from rest to the speed v requires work w. Okay? Does that make sense? And it wants to know from here to here. So how much work are we going to do to make that second jump? True. More is the right answer. All right? Let's go more specific. All right? Again, what is work doing for us? When work is done, what happens? Energy changes, right? So, how much does the energy change between the middle picture and the last picture? Does that make sense? Change is the difference between the beginning and the end, right? At the middle picture, it already has one value of kinetic energy. It went up to 4. That's a change of 3, right? It would be 4W for the whole trip, but it didn't ask us about the whole trip. It just asked us about that second interval, all right? Does that make sense? That's a little tricky one, but those are the kind of questions that show up on like multiple choice sections and stuff like that, because that's what they try to do. All right, good there? Okay. All right, let's go all the way to the back of the back page, or the bottom of the back page, and let's talk about power. Okay. All right, so as far as power is concerned, power is a ratio. Power is a ratio between work and time. The power is the relationship between work for time. How much work do we do? How much longer does it take us to do it? Or if we use when we talk about something being measured over time, we call that a rate, right? So power is the rate at which work is done, okay? All right, so that being said, let's talk about this first picture over here, okay? On the left, we have 3 people going up the stairs, right? And so it says, who or what is the most powerful, all right? We're missing a little bit of information here to technically answer this question, but if we assume that the girl on the right is running and the other 2 people are walking, what can we say about the most powerful? Who would be the most powerful? The one on the right, okay? Assuming what about all 3 of the people in that picture? They all have the same mass. Right? Is there energy increasing in that picture? When you walk up the steps, does your energy increase? What kind of energy? Potential energy increases, right? Because you're getting higher and higher and higher. So you are doing work when you walk yourself up the steps. But power doesn't just depend on work, it also depends on how long it takes to do that work, right? So if we assume that all of them have the same mass and we did mgh on them, we'd get the same answer. But power depends on how much work you do, but also how much time it takes. So the one on the right is probably probably more powerful because it's taking less time, right? Although if you examine this picture closely, it does appear that the girl on the left would be more powerful than the guy, because even though this guy is clearly trying to hit on this girl as they're walking up the steps, here, if you notice one thing, right? Yeah, it's definitely a stock photo, like no problem. But so if you're a guy and you're trying to hit on a girl, what should you probably offer to do? Carry her books, right? You know, like, hey, I'll carry those for you. So that means here that this girl is probably more powerful than this guy because she's doing more work, because she has more mass, because she has to carry the books up the steps. So probably not the best plan of action if you're looking to get a date, but hey, what do I know? So, all right, good there? All right, on the other side, right, okay, here, if we look power-wise, right, work in time, the guy on the left in his awesome ski mask, right, it definitely appears to be a ski mask that he's wearing. It's either that or he's Spider-Man. I guess that's the other option. So, yeah. What? Yeah, his dog, but it's pretty awesome. Yeah. So, in the case here, right, guy goes out and shovels his driveway and his sidewalk, and it takes whatever, half an hour. Right? The snow blower thing could also drive along the road for a half an hour, right? But who's doing more work in that time? Totally the guy, right? So, right. If we look at the dog, he's working hard. So, the dog's like, why'd you drag me out here? I was perfectly fine just sitting in the window watching the snow fall. What? So, my favorite is the dogs that have to wear coats. Like, I mean, I know.
The small ones.
Yeah, I mean the small ones because they don't have yeah, exactly. So yeah, it's like a greyhound maybe or something like that. Like, you know. So yeah. Well, it's kind of. I was actually talking to one of my kids' friends' moms over the weekend, and it's like very convoluted, but another family that we know. I just wasn't talking to that mom. So they got their kids a dog, like 5 years ago, and so it's not an old dog, like 5-year-old dog, stuff like that. Started like running into stuff. They took him to the vet. Yeah, he's blind now. Like he just has some kind of like degenerative disease, and like now the dog is blind. And you're like, okay, now I got my kids this dog, because they wanted a dog, and now it's a blind dog. But he's only like 5 years old, so it's not like he's like on the verge of passing away. Like he's still a relative. So yeah, now I have a blind dog. Great, like Say again. Yeah, exactly. Like okay, I mean. You could take him to Halloween parties as Stevie Wonder. I don't know, like, so that might be in poor taste, but you could, So. Does he have to wear sunglasses all the time? True. So, but he'd have to be deaf too, right? I mean, like, yeah. All right, one last thing on power. If we take a look, right, again, looking at some manipulations, we plug in the expression for work into power, right, force times distance over time, right, but hopefully that relationship is looking familiar, right, from a couple chapters ago, right? So we can also calculate the power that something is generating by looking at the relationship between the force and the velocity of that object. So just a manipulation, but it's still the same. It's an equivalent expression, just a manipulation that gets us power in a different setting. Good there? We'll do that. All right, so as we discussed at the beginning of class, we checked the calendar out real quick, okay? You guys do have a quiz over conservation of energy. I think it's 4 multiple choice questions, but then there's also some short answer explanation-y kind of questions that go along with it. So again, when you get your score, the highest possible score you could get is 4 out of 10, so don't freak out if you got 4 out of 10. I have to add your short answer question points into that. I have to grade those myself. So don't freak out about that. If you haven't done the previous quiz on kinetic and potential energy, literally do it now because it's 4 multiple choice questions and they're pretty easy. So get those done. Test corrections as well. You have about 10 minutes right now, so if you want to get some things done at this point in time, that'd be great. We'll start up on lab tomorrow. If we finish lab tomorrow or early on Friday, you'll have the rest of the period to work on those things as well. Okay? Good? Questions? Oh, there are some homework problems here on the calendar that are calculations dealing with work. A lot of those you will work on in your lab over the next couple days as well, so similar type questions there. All right? Be productive.